There is something quietly humbling about looking up at the night sky and realizing that almost everything you see is a memory. The stars are not where they appear to be. The light reaching your eyes left those distant suns years ago, decades ago, sometimes thousands, or even millions of years ago. You are not seeing the universe as it is in this moment. You are seeing the universe as it was, scattered across time, a mosaic of different moments all arriving at once. Here, now, in the quiet darkness above you. And in a strange way, this makes astronomy unlike any other science. We are not studying the present. We are studying the past, reaching back through time with our instruments, trying to understand what happened long ago, far away, in places we can never visit. And for a very long time, we thought we had figured out the basic story. We thought we understood, at least in broad strokes, how the universe began and how it has changed over billions of years. We knew it started in a hot, dense state, an event we call the Big Bang, and that it has been expanding and cooling ever since. We knew that in the beginning, the universe was almost perfectly smooth, with only tiny variations in density, but that over time, gravity amplified those variations, pulling matter together into clumps that became stars, galaxies, clusters of galaxies. We knew that the first stars formed a few 100 million years after the Big Bang, that they were massive and short-lived, that they seeded the universe with heavier elements when they exploded. We knew that galaxies grew slowly, merging and accumulating mass over billions of years, that supermassive black holes formed at their centers, that planets formed around stars, and that eventually, on at least one of those planets, life emerged. It was a story that made sense. It was elegant, coherent, supported by decades of careful observation and mathematical modeling. And it was not just speculation. It was grounded in evidence, in the cosmic microwave background radiation that fills the universe, in the distribution of galaxies across the sky, in the spectra of distant stars, in the patterns of light and shadow that telescopes have been capturing for generations. The story had details we were still working out, questions we had not yet answered, but the framework seemed solid. The broad outline seemed clear. And then we built a new telescope. We spent years designing it, engineering it, solving countless technical challenges. We made it larger and more sensitive than anything that had come before. We gave it a mirror made of gold-coated beryllium segments, each one polished to a precision of nanometers. We equipped it with instruments that could detect the faintest infrared light that had been traveling through space for billions of years, stretched by the expansion of the universe into wavelengths invisible to the human eye. We launched it into space, sent it far from Earth, out to a point called the second Lagrange point, 1,000,000 miles away, where it could observe the cosmos without interference from our planet's heat or atmosphere. And we named it after James Webb, one of the administrators who helped build the foundation of modern space exploration. The James Webb Space Telescope began its observations in the summer of 2022, and almost immediately, it started sending back images that were breathtaking in their clarity and detail. We saw galaxies so distant that their light had been traveling for more than 13 billion years. We saw stars being born in clouds of gas and dust, their formation captured in unprecedented detail. We saw the atmospheres of planets orbiting other stars, analyzed their chemical compositions, detected the presence of water vapor and carbon dioxide. We saw things we had hoped to see, things we had predicted we would see. And for a moment, it felt like a confirmation, a validation of everything we had worked so hard to understand. But then, as the data started to accumulate, as astronomers began to analyze the observations more carefully, something strange started to emerge. The universe that the James Webb Space Telescope was showing us was not quite the universe we had expected. It was close, but not identical. There were discrepancies, small at first, easy to dismiss as measurement uncertainties or quirks in the data. But as more observations came in, as the patterns became clearer, it became harder to ignore the fact that something was not quite adding up. The models we had built, the framework we had constructed, were not matching the reality that the telescope was revealing. Not in catastrophic ways, not in ways that overturned everything we thought we knew, but in subtle, persistent ways that asked us to reconsider, to look more carefully, to question whether the story we had been telling was as complete as we thought. And this is not a failure. This is not a sign that science has gone wrong or that our understanding is fundamentally broken. This is simply the way science works. We build models to explain the world, and we test those models against observations. When the observations match, we gain confidence. When they do not match, we learn something new. We adjust, we refine, we expand our understanding. The universe does not owe us simplicity. It does not owe us easy answers. It is what it is, and our job is to observe it carefully, think about it deeply, and try to make sense of what we see. Let us begin with something fundamental, something that touches on the very nature of the universe itself. The expansion. We have known since the 1920s that the universe is expanding, that galaxies are moving away from each other, not because they are traveling through space, but because space itself is stretching, carrying them along. This discovery was revolutionary. It changed everything. It meant that the universe had a history, that it had not always been the way it is now, that if you could run time backward, the universe would become smaller, denser, hotter, until eventually you reached a point where it was infinitely dense, a singularity, the moment we call the Big Bang. And if the universe is expanding, we can measure how fast it is expanding. This is called the Hubble constant, named after Edwin Hubble, the astronomer who first discovered the expansion. The Hubble constant is a number expressed in units of kilometers per second per megaparsec, which tells us how fast galaxies are receding from us depending on their distance. It is one of the most important numbers in cosmology because it tells us not only how fast the universe is expanding now, but also how old it is, how large it is, and how it will evolve in the future. For years, astronomers have been trying to measure the Hubble constant as precisely as possible. And for years, they have been getting different answers depending on how they measure it. Some methods look at the nearby universe. They use something called the cosmic distance ladder, a series of overlapping measurement techniques that allow us to determine the distances to faraway galaxies. One key step in this ladder involves observing a type of exploding star called a type Ia supernova, which always explodes with roughly the same intrinsic brightness. By measuring how bright these supernovae appear from Earth, we can calculate how far away they are, and by measuring how fast they are moving away from us, we can calculate the Hubble constant. When astronomers use this method, they get a value of around 73 kilometers per second per megaparsec. But there is another way to measure the Hubble constant, a way that looks not at the nearby universe, but at the distant universe, at the very edge of what we can see. This method uses the cosmic microwave background, the faint glow of radiation that fills the entire universe, left over from a time about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely through space. This radiation has a very specific pattern, tiny variations in temperature and density that reflect the conditions of the early universe. By analyzing this pattern in great detail, using satellites like the Planck mission, astronomers can infer the properties of the universe, including the Hubble constant. And when they do this, they get a different value, around 67 kilometers per second per megaparsec. 6 kilometers per second per megaparsec might not sound like much, but it is a significant difference, large enough that it cannot be easily explained away as a measurement error. Both methods have been checked and rechecked, refined and improved, and the discrepancy remains. This is what astronomers call the Hubble tension, and it has been one of the most puzzling problems in cosmology for the past several years. The James Webb Space Telescope has been used to refine the measurements of the nearby universe, to look more carefully at the distances to faraway galaxies, to observe more supernovae, to reduce the uncertainties in the cosmic distance ladder. And what it has found is that the tension persists. The number stays around 73. The discrepancy does not go away. If anything, it becomes more pronounced, more difficult to dismiss. So what does this mean? There are a few possibilities, and none of them is simple. One possibility is that there is still some subtle error in one of the measurements, some systematic uncertainty that we have not fully accounted for. Perhaps the supernovae are not as uniform as we think. Or perhaps there is something about the cosmic microwave background that we are misinterpreting. But both methods have been scrutinized exhaustively, and both seem robust. Another possibility is that our understanding of the universe is incomplete, that there is something happening, some process or force that we have not accounted for in our models. Perhaps dark energy, the mysterious force that seems to be accelerating the expansion of the universe, does not behave the way we think it does. Perhaps it changes over time, or varies from place to place in ways that affect the expansion rate. Or perhaps there is something else entirely, some new physics, some unknown particle or field that is influencing the expansion in ways we have not yet imagined. The Hubble tension is not a crisis, but it is a question mark, a gentle reminder that the universe is more complicated than our models suggest, that there is something we are missing, something we do not yet understand. And the James Webb Space Telescope, by providing more precise measurements, is not resolving the tension, but sharpening it, making it clearer, more urgent, more impossible to ignore. And this is just the beginning. The Hubble tension is one puzzle, but there are others, many others, scattered throughout the data that the James Webb Space Telescope has been collecting. And perhaps the most striking of these puzzles involves the early universe, the time when the first galaxies were forming, when the cosmos was still young, still finding its shape. According to our models, galaxies should form gradually. In the beginning, shortly after the Big Bang, the universe was almost perfectly smooth, with only tiny variations in density, ripples in the fabric of space and time. But those ripples were enough. Gravity amplified them, pulling matter together into clumps, and those clumps grew over time, attracting more matter, collapsing under their own weight, igniting the first stars. These first galaxies should have been small, faint, irregular, chaotic. They should not have had much structure. They should not have been very massive, because structure takes time to build. You cannot create a large, organized galaxy overnight. It requires hundreds of millions of years of growth, of mergers, of stars forming and dying and enriching the gas with heavier elements, of black holes growing at the centers, of spiral arms forming, of everything slowly settling into the patterns we see in the galaxies around us today. But when the James Webb Space Telescope looked at the early universe, when it pointed its instruments at the most distant galaxies, the ones whose light has been traveling for more than 13 billion years, it saw something unexpected. It saw galaxies that were large, bright, massive, more massive than they should be at that time. These were not just a few outliers, a few unusual objects that could be explained away as rare anomalies. There were many of them, scattered across the sky, enough that they represented a pattern, a consistent feature of the early universe that our models had not predicted. How did these galaxies get so massive so quickly? How did they assemble so much matter, ignite so many stars in such a short time? The models say it should not be possible, or at least it should be very rare. And yet, the observations say it is happening. Not rarely, but commonly, perhaps even typically. And this creates a tension, a mismatch between theory and observation, between what we expected and what we are seeing. There are a few ways to interpret this. One is that our models of galaxy formation are missing something, that the processes that pull matter together and ignite star formation can work faster, more efficiently than we thought. Perhaps the early universe was more dynamic than we assumed, with bursts of rapid star formation triggered by collisions between gas clouds, or by the intense radiation from the first massive stars, or by some other mechanism we have not fully understood. Perhaps dark matter, the invisible substance that makes up most of the mass of the universe, was distributed differently in the early universe, clumped more tightly, creating stronger gravitational wells that could pull matter together more quickly. Another possibility is that we are misinterpreting what we are seeing, that these objects are not as massive as they appear, that their brightness is being amplified by some process, perhaps by the intense radiation from supermassive black holes at their centers, or by unusually efficient star formation that makes them look brighter and more massive than they actually are. This is possible, but it requires careful analysis, detailed modeling, and even then, it may not fully explain what we are seeing. Or perhaps the simplest explanation is that our models, as good as they are approximations, useful frameworks that capture the broad outlines of galaxy formation but miss some of the details, some of the ways that matter can come together more quickly under certain conditions. And if that is true, then the solution is not to abandon the models, but to refine them, to make them more sophisticated, to include processes and phenomena that we had not previously considered. This is how science progresses. Not through revolutions, not through dramatic overturnings, but through gradual refinement, through the slow accumulation of observations that push us to think more carefully, to adjust our understanding, to expand the boundaries of what we know. And then there are the black holes, supermassive black holes. The enormous objects that sit at the centers of most large galaxies, including our own Milky Way. These black holes are extraordinary. They are millions or billions of times more massive than the Sun. And yet, they are incredibly compact. All of that mass compressed into a region smaller than our solar system. They grow by consuming matter, by pulling in gas and stars and anything else that comes too close. And as that matter falls inward, it heats up, glows, releases enormous amounts of energy. This is how we detect supermassive black holes, not by seeing them directly, but by seeing the light from the material swirling around them, the accretion disk, the jets of matter and energy that shoot out from their poles. Supermassive black holes are common in the universe today, but they should not have been common in the early universe because they take time to grow. A black hole starts small, perhaps as the remnant of a massive star that has collapsed at the end of its life, and it grows slowly over millions of years, accumulating mass bit by bit to reach the enormous masses we see in the centers of galaxies today. Black holes should need billions of years. And yet, the James Webb Space Telescope is finding supermassive black holes in the very early universe, less than 1 billion years after the Big Bang, that are already enormous, already billions of times the mass of the Sun. How is this possible? How did they grow so fast? There are a few theories. One is that these black holes did not start small. Perhaps in the early universe, under the right conditions, entire clouds of gas collapse directly into black holes, creating what are called direct collapse black holes, objects that are born massive, perhaps thousands or even hundreds of thousands of times the mass of the Sun, and then grow from there. This would give them a head start, allow them to reach supermassive sizes more quickly. Another theory is that these black holes are feeding more efficiently than we thought, that they are consuming matter at rates higher than what we call the Eddington limit, the theoretical maximum rate at which a black hole can grow without the radiation pressure from the infalling matter pushing away additional material. Perhaps in the dense, chaotic environment of the early universe, black holes can exceed this limit, at least temporarily, allowing them to grow faster. Or perhaps there is something we are fundamentally misunderstanding about how black holes grow, some process or mechanism that operates differently in the early universe, where conditions were so different from anything we can observe nearby. The universe was hotter then, denser, more uniform. Perhaps black holes behave differently under those conditions. Perhaps the rules we have learned by studying black holes in the nearby universe do not apply in the same way to the early universe. And this is not just 1 or 2 black holes. The James Webb Space Telescope is finding many of them, enough that it suggests this is not an anomaly, but a feature. Something common, something that our models need to account for. And again, this is not a sign that our models are wrong, but a sign that they are incomplete, that there is more to learn, more to understand about how the universe evolved in its earliest moments. And then there are the little red dots. These are strange, compact objects that the James Webb Space Telescope has been finding in the early universe, small points of light that do not fit neatly into any category. They are too bright to be normal galaxies at that distance. They are too compact to be typical star-forming regions. And their light has a strange quality, a reddish hue that suggests something unusual is happening. With the gas and dust around them, some astronomers think these might be supermassive black holes in the process of forming, surrounded by hot gas that is glowing intensely as it spirals inward, obscured by dust that rettens the light. Others think they might be galaxies undergoing extremely rapid bursts of star formation, creating stars at rates far higher than anything we see in the nearby universe, perhaps triggered by galaxy mergers, or by the collapse of massive gas clouds. No one is quite sure yet. The data is still being analyzed. The models are still being tested. Different teams of astronomers are proposing different interpretations, and it will take time, more observations, more detailed analysis to figure out what these objects actually are. But whatever they are unexpected. They are not something our models predicted we would see. They are the universe showing us something new, something we had not anticipated, something that challenges our understanding and invites us to think more deeply. And there is something else, something even more puzzling, something that touches on the large-scale structure of the universe itself. When astronomers map the positions of galaxies across the sky, they see patterns. Galaxies are not scattered randomly. They cluster together in groups, in filaments, in vast sheets and walls, separated by enormous empty voids. This is the cosmic web, the large-scale structure of the universe, shaped by gravity, by the way dark matter clumps together and pulls ordinary matter along with it. This structure has been predicted by simulations, modeled in great detail, and it matches what we observe, at least in broad terms. But recently, astronomers have been noticing something strange. There seem to be patterns in the way galaxies are rotating, in the orientation of their spiral arms, and these patterns extend across enormous distances, far larger than we would expect if galaxies were simply rotating independently, each one responding only to its local environment. Some galaxies, separated by millions of light years, seem to be aligned with each other, as if they are responding to some large-scale influence, some force or structure that extends across the cosmos. This is puzzling because there is no obvious mechanism that should cause this. Galaxies are influenced by their neighbors, by the gravity of nearby galaxies and clusters, but not by galaxies that are far away. The forces fall off with distance, becoming negligible over large scales. And yet, the patterns are there, faint but persistent, visible in the data from large surveys, including observations from the James Webb Space Telescope. What could be causing this? Is it a statistical fluke, a pattern that appears by chance but does not mean anything? Or is it a hint of something deeper, some property of the early universe, some subtle effect of dark matter, some remnant of the processes that shaped the cosmos in its earliest moments? No one knows yet. The observations are still being debated. Some astronomers are skeptical, suggesting that the patterns could be artifacts of the way the data is analyzed, or could arise from selection effects, biases in which galaxies are observed and which are not. Others think the patterns are real and require an explanation. And if they are real, they are asking us to rethink our understanding of how structure forms in the universe, how galaxies interact with each other and with the larger cosmic web, how information can propagate across such vast distances. And the surprises continue. The James Webb Space Telescope has also been studying exoplanets, planets orbiting stars other than our Sun, and it has been analyzing their atmospheres, the thin layers of gas that surround them. This is done by observing the planet as it passes in front of its star, a transit, and measuring how the star's light changes as it filters through the planet's atmosphere. Different gases absorb light at different wavelengths, creating a kind of fingerprint that allows us to determine what the atmosphere is made of, what molecules are present, what the temperature is, what the weather might be like. And what the James Webb Space Telescope is finding, in some cases, is atmospheres that are stranger than expected, with chemical compositions that do not match the models. Some hot Jupiters, giant gas planets that orbit very close to their stars, have atmospheres that are missing expected gases, or have clouds made of materials we did not anticipate, or show signs of chemical reactions that should not be happening at those temperatures and pressures. Some smaller planets, rocky worlds more similar to Earth, have atmospheres that are thinner or thicker than predicted, or have unexpected amounts of water vapor or carbon dioxide, or show signs of volcanic activity or other processes that we had not considered. This is not necessarily a problem. It is a reflection of the fact that planets are diverse, more diverse than we can easily capture in our models. Every planet is unique, shaped by its own history, its own formation process, its own interactions with its star and with other planets in its system. And as we study more exoplanets, as we gather more data, we are learning that the solar system we live in, the 8 planets orbiting our Sun, is not necessarily representative of what is out there. There are planets that are nothing like anything in our solar system. Planets that orbit their stars in days instead of years. Planets that are half rock and half water. Planets with atmospheres made of vaporized metal. Planets that are tidally locked, with one side always facing their star and the other side always in darkness. The diversity is astonishing, and it challenges us to expand our thinking, to build more flexible models, to account for possibilities we had not imagined. And there are chemical puzzles as well. The James Webb Space Telescope has been studying the light from distant galaxies, analyzing the elements present in their stars and gas clouds, and it is finding, in some cases, chemical compositions that are unexpected. Heavy elements, elements like carbon, oxygen, iron, are created inside stars, forged in the nuclear reactions that power them, and then dispersed into space when stars explode as supernovae. Over time, the universe becomes enriched with these elements, and each new generation of stars is born from gas that is slightly more metal-rich than the last. But some of the galaxies the James Webb Space Telescope is seeing in the early universe seem to be metal-rich already, as if they have gone through multiple cycles of star formation and supernova explosions in a very short time, or as if the first stars were unusually efficient at producing heavy elements. This is surprising because it suggests that the early universe was more chemically complex than we thought, that the processes of star formation and element production were happening faster, more efficiently than our models predict. And this, again, is asking us to refine our understanding, to think more carefully about how the first stars formed, how massive they were, how quickly they lived and died, how their remnants spread through the cosmos. And there are hints, faint and tantalizing, of magnetic fields in the early universe. Magnetic fields are common in the universe today. They are present in stars, in galaxies, in the space between galaxies. They are generated by the motion of charged particles, by electric currents, by the complex dynamics of plasma. But they should take time to build up, to amplify, to reach the strengths we observe. And yet, the James Webb Space Telescope is seeing signs of magnetic fields in very young galaxies, galaxies that have not had much time to develop them. Where did these fields come from? How did they form so quickly? Are they remnants of some process in the very early universe, something that happened in the first moments after the Big Bang, when the universe was filled with a hot, dense plasma? Or are they being generated by mechanisms we do not yet understand, by processes that operate differently in the early universe than they do today? These are open questions. The data is still preliminary. The interpretations are still being debated. But they are examples of the way the James Webb Space Telescope is pushing the boundaries of our knowledge, showing us things we had not expected to see, asking us to think more carefully, to question our assumptions, to expand our understanding. And there are anomalies in gravitational lensing as well. Gravitational lensing is a phenomenon predicted by Einstein's theory of general relativity, where the gravity of a massive object bends the path of light passing near it, creating distorted or multiple images of more distant objects. This is a powerful tool for studying the universe. It allows us to see objects that would otherwise be too faint, and it allows us to map the distribution of dark matter, the invisible substance that makes up most of the mass of the universe, but does not emit light. By studying how light is bent, we can infer where the mass is, how it is distributed, how it clumps together. But sometimes, the lensing does not behave exactly as predicted. The images are not quite where they should be, or they are brighter or dimmer than expected, or there are small distortions that do not match the models. These could be errors in the models, Or they could be hints of something more interesting, some property of dark matter that we have not accounted for, some clumpiness or structure on small scales that our simulations do not capture. Or they could be the effects of smaller, unseen objects, rogue planets or black holes, or other dense bodies that are bending the light in ways we have not anticipated. Again, this is not a crisis. It is not a sign that our understanding is fundamentally wrong, but it is a reminder that the universe is complicated, that our models are simplifications, approximations, useful tools but not perfect representations of reality. And as we gather more data, as we look more carefully, we find the places where the approximations break down, where the models need to be refined, where there is more to learn. And so, where does all of this leave us? What do we make of these contradictions, these puzzles, these discrepancies between what we expected and what we are seeing? Are they signs that our understanding is broken, that we need to start over, to rebuild our models from the ground up? Or are they simply the natural process of science, the way that knowledge grows and refines itself as new data arrives? The answer, almost certainly, is the latter. Science is not a fixed body of facts. It is a process, a method, a way of asking questions and testing answers. We build models to explain the universe, mathematical descriptions of how we think things work, and we test those models against observations. When the observations match the predictions, we gain confidence. When they do not, we learn something new. We adjust the models. We refine them. We make them more complex, more nuanced, more capable of capturing the richness and diversity of the real universe. And this is not a failure. This is progress. This is how science moves forward. Not through sudden revolutions, not through dramatic overturnings, but through gradual accumulation of observations, through careful analysis, through patient refinement of our understanding. The models we have now are not wrong. They are incomplete. They capture the broad outlines, the main features, but they miss some of the details, some of the subtleties, some of the ways that the universe can surprise us. The James Webb Space Telescope is giving us the data we need to fill in those details. It is showing us the universe in unprecedented clarity, revealing structures and patterns and phenomena that we could not see before. And yes, some of what it is showing us is puzzling. Some of it does not fit neatly into the frameworks we have built, but that is not a problem. That is the point. That is what makes it exciting, what makes it valuable, what drives us to keep looking, keep questioning, keep trying to understand. And there is something deeply human about this, something almost poetic. We are a species that looks up at the sky and wonders. We build telescopes, extraordinary instruments, engineering marvels, and we send them into space, pointing them at the distant universe, trying to see as far as we can, trying to understand as much as we can. We construct models, elegant mathematical frameworks, and we test them against reality. And when reality surprises us, when it shows us something we did not expect, we do not despair. We get curious. We ask questions. We revise our models. We keep trying. And in doing this, we are participating in something larger than ourselves, something that extends back through history, back to the first humans who looked up at the stars and wondered what they were, back to the first astronomers who tried to map the heavens, back to the first scientists who realized that the universe could be understood, that it followed rules, that those rules could be discovered through observation and thought. We are part of a long tradition of curiosity, of questioning, of seeking to understand the world around us. And the James Webb Space Telescope is the latest tool in that tradition, the latest way we have found to ask the universe questions and listen carefully to its answers. And the answers are often surprising. They are often not what we expected, but that is what makes them valuable. That is what makes them worth pursuing, because every surprise, every contradiction, every puzzle is an invitation to think more deeply, to question our assumptions, to expand our understanding. The universe is not obligated to match our models. It is not obligated to be simple or easy to understand. It is what it is, vast and ancient and complex and endlessly fascinating. And our job, as curious beings, as seekers of understanding, is to keep looking, keep learning, keep trying to make sense of it all. And so, when we look at the discoveries of the James Webb Space Telescope, when we see the galaxies that formed too quickly, the black holes that grew too fast, the strange patterns, the unexpected atmospheres, the chemical puzzles, we should not see them as failures. We should see them as gifts. They are the universe, showing us where our understanding is incomplete, where our models need to be improved, where there is still work to be done. They are reminders that the cosmos is richer, stranger, more interesting than we sometimes imagine, and that there is always more to discover. And perhaps, in the end, this is the most important lesson. Not that we have all the answers, but that we are willing to keep asking questions. Not that we understand everything, but that we are curious about what we do not understand. Not that our models are perfect, but that we are willing to revise them when the evidence demands it. This is the spirit of science, the spirit of inquiry, the spirit that drives us to build telescopes and send them into space, to study the distant universe, to seek out the mysteries that lie hidden in the darkness. The James Webb Space Telescope is showing us a universe that is more complex, more surprising, more puzzling than we expected. And that is a beautiful thing. It is a reminder that the cosmos is vast and full of wonders, and that we, small and brief as we are capable of understanding at least some of it, capable of asking questions and finding answers, capable of participating in the great project of making sense of the universe we find ourselves in. The contradictions do not add up yet, not completely, not perfectly, but they will in time, as we gather more data, as we refine our models, as we think more carefully about what the universe is showing us. The puzzles will be solved, or at least better understood, and in solving them, we will learn something new, something that deepens our understanding and opens up new questions, new mysteries, new puzzles to pursue. This is the nature of science. This is the nature of curiosity. This is what it means to look up at the sky and wonder. And the James Webb Space Telescope, with all its contradictions and puzzles, is simply the latest chapter in that long, ongoing story. A story that began when the first human looked up at the stars and asked why. And that will continue as long as there are humans to ask, to wonder, to seek, to understand. The universe is speaking to us, quietly, patiently, through the data, through the light that has traveled billions of years to reach us. And we are listening, carefully, thoughtfully, trying to make sense of what it is telling us. The contradictions are part of the conversation, part of the process, part of the way we learn. And in time, with patience and care and curiosity, we will understand them, and they will become part of the larger story, The story of the universe and our place in it. The story of how matter and energy, over billions of years, organize themselves into stars and galaxies and planets and, eventually, into us. Into beings capable of looking back at it all and asking how it happened. Why it happened? What it all means. And that, perhaps, is the most remarkable thing of all. Not that the universe is complex, but that we are capable of understanding its complexity. Not that there are mysteries, but that we are capable of unraveling them. Not that the contradictions exist, but that we are capable of recognizing them, studying them, learning from them. The James Webb Space Telescope is a tool, an instrument, a piece of technology. But it is also something more. It is an expression of human curiosity, human ingenuity, human desire to understand. It is a testament to what we can achieve when we work together, when we dedicate ourselves to a common goal, when we refuse to be satisfied with easy answers and demand to know more. And as long as we keep looking, keep wondering, keep asking questions, the universe will keep surprising us, keep challenging us, keep inviting us to think more deeply. The contradictions will persist, and new ones will emerge. And each one will be an opportunity, a chance to learn something new, to refine our understanding, to expand the boundaries of human knowledge. This is the journey. This is the adventure. This is what it means to be a species that looks up at the stars and asks why. And the James Webb Space Telescope, with all its puzzles and contradictions, is simply our latest step on that journey, our latest attempt to understand the vast, ancient, beautiful universe we call home.